Okay, 2.2 day 2 rates of change. Example 1, prove the difference rule. So we're finding the derivative of f of x minus g of x, and we're going to prove that this is f prime of x minus g prime of x. So to do that, we're going to use the limit definition, which is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. So you're going to do that for both of them. So the limit of delta x as it goes to 0 of f of x plus delta x minus f of x all over delta x minus the limit of g of x plus delta x minus g of x all over delta x as delta x goes to 0. And so all that's saying is the same thing as we said up there. And then for example 2, it wants us to derive cosine of x, so we're going to derive it using the limit definition. So the limit is delta x goes to 0 of cosine of x plus delta x minus cosine of x all over delta x. So if you look at this, you can find that there's a cosine identity rule that you could use. So it would end up being limit as delta x goes to 0 of cosine x cosine delta x minus sine x times sine delta x. Still subtracting cosine x on the side. And it's all over delta x. And then so after that you could split this up because they're all over delta x. So the limit as delta x goes to 0 of cosine x cosine delta x minus cosine x all over delta x minus the limit as delta x goes to 0 of sine x sine delta x all over delta x. Can you pause it? And then after that, you'll just have to simplify the stuff. So the limit as delta x goes to 0. For this first part, you can factor out a cosine x because both sides have cosine x. So the limit of cosine x, and then you'll have cosine delta x minus 1 all over delta x. And then if you factor out a negative 1 up here, you'll have 1 minus cosine delta x, and you'll find another identity or property limit rule. And so 1 minus cosine delta x over delta x, that just equals 0. So on this side, you're left with the limit of delta x as it goes to 0 of cosine x times 0. And then don't forget about the second part. So minus the limit of delta x, as delta x goes to 0 of sine x times sine delta x over delta x. And once again, there's another little property rule that you could use, and sine delta x over delta x equals 1. So that's just going to be the limit as delta x goes to 0 of cosine x times 0 minus sine of x, and cosine of x times 0 is just 0. So the answer is just going to be negative sine x.
Okay, so example 4 is the gold coin is dropped from the top of the 1,149 foot stratosphere. Determine the position and velocity functions. So the position function is represented by S of t equals 1/2 gt squared minus the initial velocity times time plus the initial position. So to find the position, functions for this specific situation. It's 1/2 g gravity, which in feet is negative 32 feet per second squared, times time squared, minus 0 because we don't have an initial velocity, plus the initial position, which is 1149. So our position function is negative 16 t squared plus 1149. And then our velocity is just the derivative of the position. So 2 times 16 is negative 32 t, and then that's a constant, so it's 0, so it's negative 32 t. For the second part, it asks for the average velocity on the interval from 3 to 7. So for the average velocity, you have to use the position function and do the final, which is 7, minus the initial, which is 3, over the final minus the initial. So you have to plug in 7 to the position function, so that's negative 16, 7 squared plus 1149 minus negative 16 times 3 squared plus 1149 over 4, because 7 minus 3 is 4. And then if you work all that out, you get 365 minus 1005 over 4. So that equals, actually this is a positive, so that equals negative 160 feet per second squared. Part C is finding the instantaneous velocities when t equals 3 and 7. So instantaneous, you just plug it into the equation. V of 3 equals negative 32 times 3, which equals negative 96. V of 7 is negative 32 times 7, which is negative 224, and both of those are feet per second, feet per second. And then for D, it asks how long does it take to hit the ground. So it hits the ground when the position function is 0. So negative 16 plus t squared plus 1149 has to equal 0. So you just do algebra and divide by 16. And then t squared equals 1149 over 16. So then you just find the square root of that. So t equals square root of 1149 over 4, because the square root of 16 is 4. And that is in seconds. And then finally, part E is find the velocity at impact. So at impact is when it is at the ground, so that means 0. I mean, not when the position is 0, so that means that it equals this. So V of the square root of 114944. So plug that in. It's kind of ugly, but if you have a calculator, that will equal negative 271.1732 feet per second. Okay. Are you going? Okay. Area of a circle is pi r squared. To find the derivative with respect to the radius, it's 2 pi r. Simple. Great. The volume of a sphere is 4 over 3 pi 3r cubed, and the derivative of that with respect to r would be 3r squared pi 4 over 3, but then the 3's cancel out, so you're left with 4 pi r squared. And then you can...
Alright, so you're looking for the derivative, and an easy way to do it is if you just look for what the function is. So remember, it's f of x plus h minus f of x, so your function is just x to the 7th. So if you're looking for the derivative of f of x, you drop the 7 down, x, and then to the 6th. And so that's your answer for that first one. And then for the second one, it's the same thing. It's sine of pi over 6. So your function is sine of x. X is pi over 6. And then first you would derive x first. And so that's cosine of x. And then you just plug in your x. Cosine of pi over 6 is root 3 over 2.
Okay, so compare the graphs of f of x and f prime of x for f of x equals x squared. So at 1, it'd be at x equals 1, y would equal 1 as well. So you go 1 and then 1. But if it's 2, x is 2, y would equal 4. So you go 1, 2, 1, 2, 3, 4. And then the same on the other side. Then you have this parabola. Amazing, right? But then f prime of x is 2x, which is a line which is way different than this one. Here it's decreasing, and so is it here. And then increasing and then increasing. Beautiful.